section 5.5. I think I might have written 5.4 on the other problems, but anyway, this is 5.5. We're going to use substitution, and there's a whole list of ordering of like what you should let u equal. And there's some mnemonic expression, an acronym, which I don't even remember, lipid, or I never learned it. One of my students said, but anyway, there's an ordering what you should consider for letting u equal when you use substitution. I just noticed that if there's an ln, I'm going to consider that. And part of what you're going to look for is, you're going to look for the derivative ln x, which is 1 over x. Now, I do see x over here sort of by itself as a factor in the denominator. And so what I can do then is, let me just do it over here so I don't use so much space. I'm going to write e to the fourth. I'm going to write 1 over square root of ln x, but this time when I do that, I'm going to write it as to the half power. Then I'm going to separately write times 1 over x. Now that's all true. But why would I do that? Why would I separately write 1 over x? Because that's the derivative of ln x. Okay, so we see that over here. So what's going to happen, or what happens now, is that 1 over x dx is du, ln x is u. This problem is a definite integral and it has bounds. So let's change the bounds. You don't have to, but I'm going to do it. You can ignore the bounds completely, and then later on, when you substitute back for x, you can reintroduce the bounds, but I want to change them. When x equals e, u equals ln of x, and that's ln of e. So I'm starting off with this bottom bound of e. And ln and e cancel out and give 1. When x equals e to the fourth, u equals ln e to the fourth. ln and e cancel out, and I get 4. All right, so that was sort of a topic that we talked about briefly in other videos, or discussion in classes, is that logarithm and exponential functions are inverses, so when you do a composition, they cancel. So now when I make this substitution, I'm going the whole thing. I'm doing the whole thing, e. So I'm going, see, notice there's e and e to the fourth. Right, I have e to e to the fourth, but now I'm going to u equals 1 to u equals 4. See, these are x values, x equals e and x equals e to the fourth. I want everything to be u. Then I'm going to have 1 over u to the half, and then 1 over x dx is du. Now, the advantage of this, why I like this, is I'm done thinking about x's. I'm not going to substitute x back in, or I'm not going to, when I'm done, I'm not going to put u equals ln x. I'm done with x. At this point, I could, in fact, just plug in this into Wolfram Alpha or some computer software and evaluate that limit. So I don't need to put x in. Not limit or derivative, that integral. I can evaluate that integral all by itself without thinking about what u is. So I sort of like that. Now I have u to the negative 1/2. I add 1, I get u to the 1/2. Divide by 1/2. Some people just right away multiply by the reciprocal of that 1/2. And I'm going to go from 1 to 4, which turns out to be not so bad. Okay, the reciprocal 1/2 is 2. And I'll put 4 to the 1/2 minus 1 to the 1/2. So it's 2 square root of 4 minus square root of 1. So it's 2 minus 1. That's equal to 2. It's a pretty good problem. Okay, let's stop there. Any questions about that? So I change the bounds whenever I have a definite integral. You don't have to. What you can do is you can completely ignore e and e to the fourth. Just don't even think about them. You integrate, and you get this 2. Let me just show one more step of simplifying. You integrate, which is that I'm going to multiply by the reciprocal. So 2 u to the 1/2 from 1 to 4. So you integrate, and you get this 2 u to the 1/2 from 1 to 4. And then at that point, you could put in u equals ln x, but don't put 1 and 4. You would put e and e to the fourth. So anyway, that's a little bit messy the way I did this. Or it's just a little bit cramped. Okay, so let's stop recording.